or on this computer. Okay, cool. So here we are. I put a lot more content on the YouTube channel this week than I usually do. And the reason for that is because this stuff can be confusing. It usually is. It's just usually confusing. The good news about it is anyone can get it. At least I think the most useful tool aspect of what we're going to talk about next is I'm batting 1,000 with it. You know, you can the simple tools, the simple insights that you can get out of this modeling, you can do it even if you are not super psyched about math. And just so you are warned, there is some math coming. It's really not that. I'm not going to. It would be a mistake for me to downplay it. It just, you know, there's some math coming, but it's we've done well with helping students get some insights out of it, get some practical tools. Like I say, there's a lot of content on the YouTube channel. It's like 8 individual videos, and it's all a review of what I am talking about here. So if you want to see it in a different way, and the way that I usually like to teach this is to do this as a chalk talk, and I'll show you why. But I like to do this as a chalk talk, and you know, or a dry erase marker thing, because it's just easier to kind of show the individual parts, and especially the things that are I think are most useful to pay attention to. So like I say, there's 8 videos on there, and you know, they're just there so that if there's part of this content that you want to go back and look at multiple times and you want to see in a different way, then it's there for you. And if you get it and you don't need them, like, cool, right? You can save those 3-minute sections of your life for something more useful, like writing those papers. Okay, so anyway, it's review. So where we left off last time, and I'm just going to jump straight into this, is about what we want to do here is start talking about more realistic systems. Construction, sorry. I'm going to close this. They're like, they took a break, but then they started pounding away on something outside my window. What we're trying to do here is start to model systems that are more realistic, so more than one species. And one of the lessons of the Kaibab Plateau and the Kaibab deer population dynamics in the beginning of the last century is that if you remove the factors that control a population of species, you can end up changing all sorts of aspects of the ecosystem. I mean, that's the main lesson about this paper. Get rid of all of the predators here, and then you end up transforming forest structure for decades, hundreds of, probably centuries, really. So anyway, here is a framework for looking at the dynamics of predators and prey. And remember, the reason that we're interested in this is because these prey oftentimes will attack forest trees, they will attack regeneration, they can change forest structure in a way that is problematic for us. They have value themselves too, especially Kaibab deer population, they were famous. That's part of why the predators were removed, which is turned out to be self-defeating. But anyway, so we have here some dynamics for our prey population. It's denoted V. Look at that. It's exponential growth. And then we're just conditioning exponential growth on some efficiency by which predators are consuming prey. And the thing that's really characteristic about this this model is that there are 2 populations. There's a prey that's here, and there is a predator. And you explicitly have the prey appearing in both equations and the predator appearing in both equations. What that means is that these populations are linked. So there's exponential growth here, but it is conditioned on this other population. The other population is also nonlinear growth here. And there's some really amazing things that come out of this in terms of a model system. But let's go and look at it. So one of the things that I want to introduce you to now is this characteristic called an isocline. All right, and an isocline is a relationship that happens in something called phase space. So I am dumping jargon on you right now. A phase space is not the kind of graph that you are accustomed to looking at. Here, you've got the two populations appearing in the XY space. So time, we're used to looking at XY figures, and there is time here, but time isn't exactly, it isn't rendered in a very explicit way here. Instead, we've got the number of predators here on the y-axis, and we've got the number of victims. And what we're going to end up doing is describing the number of prey, the victims, as a function of predators and vice versa. So one of the interesting things that happens here is when you put any model that has more than one species into phase space, you can identify these points where the growth rate of that population is 0. That's called an isocline. So this is saying that the change in the prey per unit time is 0. It's level, it's constant, it is unchanging at that particular moment. And here in this one, this is defined by the rate of growth of the population growth rate for the prey divided by the rate that they are consumed. That's how it's defined here. And what's happening here is that if the prey population gets larger than this number, then it starts to decline. It starts to come back down. But if it is smaller than this number, then it increases. So I'm going to address why that is, but I want to acknowledge that this kind of isocline exists in the same space for the predators as well. And here it's the rate at which predators are killed. That's the Q divided by their efficiency in converting prey into new predators. Okay, so here, when the number of victims of prey is larger than this level, then the predators are going to increase. And when it's smaller than this level, the predators are going to decrease. This is just a characteristic of these models. And what that means is you end up getting this sort of cyclic dynamic like here. And so here you've got the predators and prey are abundant, and the predators are going to increase. In fact, in some ways, they're both. The predators are increasing here, and the prey are actually decreasing. Because if you have a lot of predators, they're going to eat a lot of prey. You go over into this quadrant, and they both start to decrease. And then once you get down here, the predators have decreased so much that they become scarce, and then the prey start to grow exponentially. So they start to recover, and then here they're both actually increasing. So this is like in this phase space, you get this cyclic dynamic, but here's what it actually looks like in time. As prey go up, there are more prey to be consumed, so the predators eat them and they are able to reproduce more. That makes intuitive sense. You know, that's what's happening here. So you get the prey going up, but once you have too many predators, they actually start to drive down the population of the prey. So you get this cyclic dynamic where you have this oscillating, peaks and valleys of prey, and then you have this peaks and valleys of predators too. And the only difference here is that they are out of phase. The predator population is somewhat lagged behind the prey because they're increasing while the prey are abundant, But once the prey becomes scarce, then there's this negative feedback on the populations. Okay, so if you've seen this before, this is the famous example. This is the snowshoe hare and Canada lynx. So this is the Canada lynx, pretty amazing cat. And let's just watch a little video of it. This is on the Canadian Wildlife Service website, and that's so awesome. Let's watch it again. Let's just look at this thing. Look at this. It's so great. Oh, I gotta pause it. Oh no! Oh, this is terrible. I gotta pause this. We have to just. I mean, this is more fun when we're actually together. But you know, look at this guy. Look at this guy. That's so cool. I mean, lynx is like, it's actually kind of it's a bigger cat than I thought. I thought it would be like a bobcat size, but it's a bigger cat than I thought. It's smaller than a mountain lion, but it's a pretty big cat. And wow, what a beautiful animal. You can download these videos from the Canadian Wildlife Service, and there's some really great videos. There's like ones like this. Lynx walking around. There's some other where it kind of sniffing the camera. Other ones where it takes a giant crap right in front of the camera. You know, I don't know how they worked that one out, but I don't know. You know, anyway, there's all kinds of fun on the Canadian Wildlife Service webpage. So the reason that that I want to talk about this specifically is just to show that in real systems you can have this kind of oscillating dynamic. And this is a pretty kind of famous data set that was collected by the Hudson Bay Company, and it's the it's showing how many of each of these animals was trapped, but the number of pelts that were being collected were kind of more or less following this predator-prey dynamic, and they're out of phase. Now, since this, there's been a lot of analysis of this data, and it's been since shown that the prey, the lynx, or the snowshoe hare are actually also limited by climate dynamics, the abundance of forage, and then that in turn affects the Canada lynx as well. So that, you know, of course, reality is more complicated than these simple models. However, the system overall has this behavior, this oscillating behavior that tends to be somewhat out of phase. So, why are we talking about this? Well, because herbivores can do a lot of damage on regeneration. I don't think we have anyone from Santa Cruz in our class. But people in Santa Cruz had an explosion, maybe still does, an explosion of deer, particularly in the 90s, that were decimating the regeneration of bay laurel. So bay laurel, when it's young, and this is a photograph of this, this is some bay laurel that's all been cut for a management project, a management experiment. But when it's been cut and it resprouts like this, this is really great deer forage. The deer love it, and bay laurel will be extensively browsed by deer when the shoots are young. So much so that, and I've done a lot of work at this site. It's called J. Smith State Park in Humboldt County. You'll go out to these places, and the resprouts would be like sculpted like hedges and stuff because there's been so much herbivory on it. Anyway, in the 90s, Santa Cruz had problems with having adequate regeneration of bay laurel because there was so much deer browse on it. So, you know, even locally, your herbivores can have a big effect. And the thing that I'm kind of forgetting to mention here is, why was there so much browse by deer? Because nothing was controlling the deer population. Have any of you shot a deer? Anybody? I'm just saying with heads wagging no.
I shot at one.
Ugh! And he missed.
Yeah, definitely missed.
Okay, well, thank you for your efforts. Please go and try again.
I will do.
You know, in lots of parts of the country, we need to do something about our deer population. It's the populations are not very healthy because they're too big, and they're too big in part because we've removed the predators. And in places like Pennsylvania, Kaibab Plateau and Santa Cruz, at least during the 90s, you know, it affects forest structure. It has a real impact on the things that we care about. You know, in thinking about forest ecology. So go shoot a deer, or help raise a predator that will eat more deer than you will shoot. Okay, great, cool. Predator-prey dynamics, and I get asked this a lot. Predator-prey dynamics can be related to herbivory. Sometimes you can model herbivory of trees by these Lotka Volterra dynamics. Oftentimes we use different models that are more appropriate for insects and more appropriate for diseases. And this is one point in the class where I want to acknowledge the existence of pests and pathogens, and also that they kill lots of trees. This is El Cap and tree ponderosa mortality in Yosemite Valley. It's been extensive because of bark beetle. And this is cowrie dieback in New Zealand, which is also a real major management concern down there that's related to an invasive pathogen. So anyway, the dynamics are related. We actually end up using different models for studying these dynamics, but I just want to acknowledge that they exist. Okay, so here we are. We've removed the predators. Here we are on our timeline. We've removed the predators, and then our deer population explodes. We get up here into this point where population dynamics are constrained by resources. So they run out of aspen to eat. They run out of everything to eat. And then their populations crash in a really, really ugly way. You know, starving animals is just not pretty to look at. And since then, you know, we've had better establishment of predators, reestablishment of predators, and better regulation of hunting. In particular, I think it's the 40s through 60s, there was just a lot more hunting on the Kaibab, and that was necessary. Now, I think, you know, there's just a better appreciation of the importance and benefit of predator populations, and at least the mountain lion are back. Wolves are not back here. The wolves are not back in Arizona, not as far as I know, but the mountain lion are there. You know, I grew up in rural Arizona. We had mountain lion. I've only seen one time in my entire life, and not in Arizona. But anyway, okay, but you know, again, there's here's a couple things just to kind of I've already alluded to, but just kind of show you. We're all about empiricism here and inference. This is kind of interesting. These are these corrals. These are areas that would have naturally been protected from browsing. And then, you know, there's these repeated photographs because they were located near guard stations. And you can see the change in forest structure over time, and in particular, this dramatic regeneration and establishment in the overstory of Aspen. Interesting, this, and I'm kind of glossing over this, but the title of this paper, you know, was Aldo Leopold right about the Kaibab deer herd? Leopold is one of the great minds of land stewardship and land conservation in American history, I guess I would say. Very influential thinker, and he's got an interesting story. He spent his early years, among other things, shooting predators in southern Arizona, so shooting wolves and mountain lion for the federal government. And then later on in life, he realized, well, maybe we're making a big mistake. And he looked at the Kaibab deer eruption as evidence that predators are good for us, and having predators is a part of responsible forest stewardship. But there were some questions about his data and the rigor of the data that he collected, and so that's why this group went out and tried to ask, like, can we confirm what he was thinking? And I think that they do, by and large, show good evidence that both the eruption of the deer population as well as the change in forest structure are tied together, and that removing predators from the plateau caused a lot of problems. It's very unfortunate. I think that these are problems that could have been avoided, both in terms of maintaining this amazing deer population and just maintaining the health and productivity of the Kaibab Plateau, which has value as well. Okay, so what I want to do here in the last part of this paper, and like I said, I really like this paper because it illustrates all 4 models that are of interest to us. And the last one I want to talk about is competition. One of the most central and influential factors that shape forest structure and forest dynamic. And so we're talking about 2 species. 2 species need the same resource, but they're not eating each other. So they're not directly killing each other. And this is just, you know, this grandmaster I think he's playing a computer. I can't remember. Anyway, you know, so I don't know if that's the right analogy for competition, but, you know, most of the time we're talking about this. How do trees interact with each other in terms of competition for limiting resources? And this is one thing that I think is kind of just sort of, we can get this out of the way and just acknowledge that these competition models work for they're general, that they're not just about trees, they're about, they can be applied in many different settings. This one's kind of interesting, and just wrapping up that anecdote about Yellowstone and wolves. When wolves were extirpated from Yellowstone, they were by and large replaced by coyotes. And with wolves back in Yellowstone, they're now competing with coyotes, and then they're oftentimes eating them. So anyway, that's a cool story, right? Yeah. Okay. Back to forest structure. The other thing that's really nice about this is that we can start to talk about forest communities in a very explicit way. And we can start to ask those questions. Why do we have the diversity in stands that we have? Under what conditions can we expect to have varying biodiversity within stands? And if you understand the mechanisms that create that biodiversity, then you can do things to either change it or protect it. Usually that's our management goal. We want to remove we want to remove species that are non-timber species so we can increase growth of some target species like Douglas fir, or we are trying to maintain that diversity because that's how we retain wildlife and other non-timber resources. Okay, so it's got practical value. Okay, so you know we're gonna have this framework where a single resource is limiting population growth, and the organisms are going to compete with each other. The assumptions here are, and we do this in very simple, we keep our models simple so that we can get some, so we can understand, we can get some simple insights. Real systems are more complicated, but real systems are more complicated to the extent that our models are not full representations of them, but that is fine. All models are wrong, but good models tell us something about how real systems work. All right. So yeah, here there's a single resource and there's perfect overlap. That's of course not how real systems work. They're messier. But this is an example from the Klamath region where you've got Douglas fir and tan oak competing for similar resources. They're their canopies are intertwined with each other, but this stand is managed pretty extensively, and so it's got open areas and stuff. Like reality is just more complicated than these models, but be that as it may, they still tell us something useful. Okay, so the basis that we're going to use here is our constrained growth, our logistic growth. So if you remember this, it's exponential growth, but then it's conditioned on a carrying capacity. So it tops out. The Douglas fir doesn't grow across the entirety of the earth, and it doesn't increase into infinity in terms of density or basal area in a stand. It's capped by the amount of water, light, and nutrients that are there. This K parameter is the intraspecific competition, the competition that occurs within species. Douglas fir competes with itself as well as the other trees that are around it, as well as with tan oak. So intra-A, within species competition. However, it's like I say, it's also competing interspecifically, so between or within or among species. And we're going to add that to our model here because it's missing in this example. All right, so how do we do that? Well, we add a little function here that is going to be the negative effects of interspecific species competition on our species of interest. So without that, this just reverts back to this logistic growth. If you take away the second species, you just get logistic growth. But when you add this, then when you add a second species, you've got now two different intraspecific species competition parameters, as well as two different interspecific species competition parameters. And then this is what this actually looks like. We just denote the effects like this. This is gamma and this delta. You can the notation, the Greek letters that I'm using here do not matter. We just need some way to keep it straight. That's all I'm doing here. I'm just putting in unique things. You know, and here's where we're trying to get to. Here's a picture of a coast live oak forest in Marin County. There are many species that are coexisting here: coast live oak, bay laurel, madrone. There's even occasional tan oak in there. And this is an example of like, how does that happen? How, even though they're competing within species and between species, how can you get this? This is very common. It's very common in coastal California to have mixed species stands. How does that happen? I'm going to show you one way that it can occur. Okay, and here's another example. Here's, this is a good example of intraspecific species competition. This is Douglas fir in Marin County. It's invading a grassland, but you can see the stand is really, really dense. It's got lots of intraspecific species, strong intraspecific species competition dynamics within there. Of course, the trees are competing with the grasses also. And in Marin and Sonoma County, the lack of fire, removal of fire from the landscape, has led broadly to loss of grassland ecosystems, probably because the fire would favor those open conditions. So this is a problem in many places, in many parts of the state where we have invasion of grasslands. We've lost grasslands, and we've been replacing them with forests, and especially Douglas fir. Douglas fir is just really good at that. And excuse me. Despite that Douglas fir is a very valuable timber species, it does not grow with very good timber characteristics in these settings. It grows like crap. It grows like with lots and lots of knots and stuff, really lots of branches. So we end up kind of growing like pretty crappy Douglas fir in these areas, and it's expensive to get rid of. All right, here's another example. Here's Douglas fir competing with tan oak. And again, it's just like a lot of reasons to kind of try to figure out competition or how it's occurring and when it's occurring, because this is a fuels problem. It's also a timber production problem. You know, this is a stand that was supposed to be managed for Douglas fir growth, and it's not fire safe, and it's not growing timber. So, okay. So, one of the reasons for showing the isoclines before with the predator-prey dynamics is because we can depict the same relationship, the same phase space relationships and isocline dynamics in this two species competition model. So this is the math. You can just kind of acknowledge it and let it go. The thing that's really helpful here is that I'm going to show you a way to draw these isoclines. So the isocline, remember, is the point where growth of that particular species is 0. So above this isocline, growth rate would be negative. We would have negative feedback that would decrease the population size, and below it, we would have positive feedback that would increase the population size. So down here, we have 2 isoclines here, and down here, both species are growing positively, and then up here, both species have negative population growth. What is going on here in between? Someone with their camera off, speak. Smart. I'm going to call on, so, oh, yeah, Trevor, all right, yeah. I'm gonna call on you. I gotta do this more often. Okay, Grant, are you there?
Yeah, I'm having trouble getting this one.
Okay, okay. All right, that's cool. That's acceptable answer.
Get over here.
How about Ben? What do you think, Ben?
I'm not too sure about this one either.
Okay. Oh, yeah.
Other species competition? I don't know.
Okay, cool. All right. Yeah, you know, just gotta give some relief to the people who have their cameras on. I'll give you the answer. All right, that's acceptable. That's acceptable answer. So let me just talk about how you draw these isoclines. And this is the hard part. It's just kind of confusing. What we've got here is species 1 on the x-axis. I mean, so it's hard to pay attention to when we're in a classroom and I can like walk up to you and then like point at you or tap on the table or otherwise annoy you. And it's way harder like this, right? That's why that's why I did all those videos, so that if you're confused, you can go back to them and hopefully they'll help. What we do here to draw these isoclines is we need to know 2 things. We need to know the strength of intraspecific competition and interspecific species competition. And when we know that, we can figure out where the isoclines are. So in both cases, here's species 1 here, and species 1 has some carrying capacity. And so we note that on the axis for this first species. The same thing is done for species 2. So let's say that species 2 has a lower carrying capacity than species 1. We mark that there. The other end of this is going to be for the interspecific species competition. And this is the amount that species 2, this is the point, the amount that species 2 is limited by species 1. So the strength of interspecific competition for that species. And then we denote the same thing up here. All right. So growth rate is 0 here. Above this, growth rate is negative. Down here, this is again 0. Growth rate is positive. And what is going on in between? All right. Here it is. Here it is again. Let's just see. Yeah. Okay. I'm gonna go back. And now we've got this problem. What is the growth rate of each species in that space in between? So you can just, why don't you do this? In the comments, just tell me, For species 1 in that space, tell me if you think that it's positive, negative, or 0. I'm going to just look at the chat. Put something in there. Species 1 would be negative. Negative, positive. Okay, got Ben saying positive. I've got a lot of negatives. So species 1. This is species 1 here. This one, the blue one. This is the isocline, so it's 0 here. Okay, Caitlin says it's positive. We got Ben saying it's positive. Most of you are saying negative, right? So species 1, the growth rate is 0 on the isocline. Those of you who said positive, I'm just going to give you the first refusal. If you don't want to answer why you said that, okay, but I'm just going to give you first refusal. One of you who said positive, why did you say that?
Is it positive to, like, I thought it was positive, like, down and to the left of that line and 0 on the line?
It is 0 on the line. And I actually mentioned that it's negative above it.
Right.
Because, and look, when you're above this, you've exceeded the carrying capacity. So when you exceed the carrying capacity, growth rates become negative. So this blue one, which is first species, it's actually got positive growth rate here. So here's a question. This red one, what is its growth rate in this space in between? Go ahead and answer. Species 2. Answer in the text. Good, good. 100%, 100%. You guys are great. It's negative, right? When you're above this line, the growth rate is negative. And what's happening here is in this area, we're still above the red line, so the growth is negative. We are above the carrying capacity for the second species, and so that's going to have a negative feedback on its population. But the problem we have now is that the first species, 1, has a positive growth rate, and the second one has a negative growth rate. That leads to competitive exclusion. This system is going to grow to the carrying capacity of species 1, and it's going to turn into a single species system. The second species is getting outcompeted here because the first species has less intraspecific species competition, or it's less strong, it has a less negative feedback on it, and it is a better interspecific species competitor. So if we switch this around, you know, I mean, if you have, say, species 1 as a lower carrying capacity, the question of who wins switches. So if you know the carrying capacity for a set of species and you know their interspecific species competitive effects, which is hard actually to quantify, but if you knew that, you could say, well, how is this system going to change? Will it maintain its diversity? Which species is going to dominate? That's really valuable if you're trying to grow a particular kind of species. Like if you're trying to grow Douglas fir in a place and it's going to get outcompeted by something else, like you're gonna want to know that. Maybe you don't want to grow Douglas fir there, or you're going to have to do something in order to protect the trees that you're trying to grow. Right? That's the practical part. That's the practical part. Okay, so let me go on here. Now we get more complicated. This one is, again, we've got the carrying capacity species 2, carrying capacity species 1, and then we have these coefficients for the interspecific species competition. And what's happening here is the lines are crossing. So who wins here? Up here, both species are above the isocline, so they're both negative. They're both growing negatively. Down here, they're both positive. So they're both growing, they're both having positive population growth. But here, is some trouble. Here's some trouble. This one is, species 1 is going to have negative population growth, and species 2 here is going to have positive species population growth. So species 1 is going to grow to its carrying capacity, and then it's going to have 0 population growth. This one's going to grow to, it's going to grow positively, but it's going to get to this point where it is then limited by interspecific species competition. So what happens here? What happens here? Who wins? Go ahead and do it in the chat again. This is you know, perfectly fine tool here. Who wins? Ooh, neither. Maddie, what do you mean by neither? Do you mind telling us? Do you mind unmuting and telling us? Because I think that that's an interesting answer.
Well, I mean, eventually neither of them are going to benefit because, I mean, in that small portion would neither of them benefit that we were talking about, because they're both negative and then they're both positive, and then there's this weird portion of the graph. It just seems like something not productive is happening.
Yeah, weird things start to happen in these quadrants. That is right, and I think neither is it's an interesting answer. It is, you're almost there. You're 95% of the way there. What happens here is that when you have really strong intraspecific species competition, once the populations get small enough, these each species is more controlled by competition within species than between species. And the result of that is that both populations will grow to this level. They will grow to this level and they will hang out there. So high levels of intraspecific species competition stabilize communities. You will have what is called stable coexistence here. So without any, in some perfect universe, which doesn't exist, of course, where there is no other influence here, they are all, as Nick Catelli put it in his book, all roads lead to Rome. Basically, the system is always going to grow to this stable point, and you get stable coexistence of species in a stand. It's actually really pretty hard to get rid of a second species here. You'd have to really try, because what this predicts is that you're always going to have more than one species. You're going to have biodiversity in this stand. Okay, here is the more complicated one, even more complicated. And again, the lines are crossing here, but you've got the carrying capacity here for both species is really high. And what that means is that the intraspecific competition is really low. There's not that much of it. But at very small, relatively small population sizes, interspecific species competition is really strong. So down here, you're below the carrying capacity and below the isoclines. So both populations are going to grow positively. And up here, they're both going to grow negatively because they're both above the isocline. But when you're here, you're below the isocline for species 2, but above it for species 1. So species 2 is growing positively and species 1 is growing negatively. Here, same thing happens, except species 1 is growing positively and species 2 is growing negatively. So in this quadrant, which species wins? Who wins? I'm watching the text. Okay, good. Got a vote from Joe. 2. Is that it? Or did Maddie say neither again? Okay, someone besides Joe tell me who wins in this quadrant. 2. Okay, 2. All right, good, good, good. Okay, this is called what's it called? An unstable equilibrium. Up here, like I say, you're above the isoclines, you're going to have negative growth. Below here, you're going to have positive growth. But in these 2 quadrants, you got varying outcomes. And what will happen here is that you will actually have competitive. There's an equilibrium here, but it's an equilibrium that's like standing on the head of a pin. You know, if any slight perturbation will push the system off the head of the pin, and that can send it in a very different direction. So what will happen here in general is when you're in these quadrants, whichever species is more abundant will win. You'll have competitive exclusion. And the reason for that is because the more of species 2 that you have here, the greater the effect of interspecific species competition. Because each individual of species 2 has a negative impact on the first species. So when you have this kind of situation, you can predict which forest tree will dominate your stand. If you know the carrying capacity and you know its relative competition with another species, maybe something that you do or do not want in that stand. You have a practical tool for predicting whether you're going to have coexistence or whether you're going to maybe even lose the species that you care about. These do seem to exist in nature, and they're actually an important part of maintaining biodiversity because even though they're unstable, there are many factors that affect the ecological dynamics of forests. You know, their climate varies in time. You have an bark beetle outbreak one year, all kinds of things like that. They're still important for biodiversity, even though they're not as stable as when you have strong intra-specific species competition. All right, so that's the promised practical thing. So here's our, this is how I want to wrap this all up. You know, Kaibab Plateau, what happens when you remove all the predators? Well, you end up with a lot of trouble. But we have this interesting thing that happens here. You know, we remove all the predators, the deer population erupts, and we lose all the aspen regeneration. But here, this is what I want to bring your attention to. Here, in recent decades, particularly through the 70s and 90s, you have a tremendous increase in aspen regeneration. What happened? You all forgot already. I mean, I get it. You know, you kind of read this thing and you're like, brain dump, I have to go write another paper. Seriously, what happened? Because this is way more regeneration than occurred beforehand. So what happened?
Did interspecific competition decrease since between different types of species?
Yes, you are on the right track. Interspecific species dynamics were greatly changed across the entire Kaibab Plateau. That is what you are seeing here. You are seeing the effects of removing interspecific species competition on aspen. What was it?
Logging, I believe.
It was logging, right? Yeah, and aspen isn't really that valuable of a timber species, but ponderosa pine is. And during these couple of decades, there was more extensive cutting of ponderosa pine, and that changed the competitive dynamics. So what I love about this is, like I say, we have all of the population dynamics, the typical population dynamic models that we cover in a basic ecology class, but it's all in the context of forests. including predator-prey dynamics. So anyway, that's why I'm a fan of this. Plus, it's just, I don't know, I just think it's pretty interesting. And, you know, you can look at this whole 2 centuries of forest dynamics here, and you can point to different parts of it where forest cover and forest regeneration is controlled by different factors. I think the other thing to walk away from this with is what we do matters. What we do matters. What we do as managers matters. It changes the structure of forests, and we need to be able to answer the question of whether we want those are the changes we want or not. So, you know, things that like problematic fuel levels, or in general a reduction in timber, those kinds of things, those are oftentimes predictable, and it is incumbent upon us to answer the question whether we want those changes or not. Cool. So yeah, you know, here's this, you know, this is the logging. This is just the logging rates that they have in there, and you know, you can see that they do spike, and you know, I'll just kind of pull this back here. You know, like I say, these kinds of things we should be able to predict, and when we stop burning, then we're going to have shifts in competition. They're going to create some other problems sometimes. I should also point out, this is a photograph from Marin. The agency here is working to restore this grassland, or at least to reduce this problematic fuel condition here. So they're actually spending quite a lot of money to get rid of the of this Douglas fir. I'm hesitant to call it timber because it's worthless. Basically, nobody's winning here. This is just a real problem. It's an expensive problem to clean up. And then we have lots of other places that are just densified from various reasons, including prior harvesting. And, you know, cleaning it up is expensive. Running this equipment is really expensive. I mean, you know, this kind of fuels management can be as much as, you know, $10,000 an acre. $10,000 bucks an acre. It's expensive. I mean, it works. You know, this equipment works. Like, this machine just gobbles up all this live fuel and the dead fuel too. But it's a lot. It's hard to do. It's expensive. The machines are expensive. The operators, the fuel, everything. And like I say, it works. You end up with this mulch, and it's the fire hazard conditions are a lot lower. So anyway. That's what I got for you. It's I know that's a lot. I know it's a lot, and I know it's a lot because when we're in the classroom, there's a lot of blank stares, and I know that it's going to be worse now. Okay, so we're going to carry on with the class, and I am going to find ways to come back to this material, because under the best circumstances, I always have to go through it more than once. Okay, so anyway, at least it would be easier if we were doing this on Zoom, but at least, you know, I know that it's harder, so I've got to find it. Okay, I'll stop the recording. That's right.